Hello, good evening and welcome. I'm Neil Johnson. I'm the chair of the Audio Engineering Society Cambridge Regional Group and host for this AES UK section webinar. Is digital audio really as good as it could be? Did we miss some key concepts along the way? Are we missing out more than we think? In tonight's talk, Bob Stuart from MQA will take a bird's eye view of auditory science, wander through the fields of sound recording from analog to digital, dabble in the 7 theories of high resolution, and consider the paradoxes of losslessness and data versus information flow. This talk will show that by more precisely defining our objectives, then a better engineering solution to sound recording and playback is indeed possible. Bob's talk will begin in a moment. He is happy to answer any questions you have, so feel free to use the Q&A button at the bottom of the screen to type your questions in, and we will go through those at the end. Tonight's talk is brought to you in cooperation with the Institution of Engineering and Technology Cambridge Local Network. I'd like to take this opportunity to welcome both AES and IET members across the world to this evening's webinar. And now, without further ado, and less from me, it is my pleasure to welcome Bob to the stage.
I'm delighted to be here. It's somewhat unusual, actually. Although I'm used to giving talks, I've never once given a talk only to my computer. But I see actually there's almost 500 people there. And I think, Neil, when I agreed to give this talk, well, there are going to be 20 of us in a hall in Cambridge. But never mind, this is fun, and we'll look forward to the questions at the end. As Neil said, this is really about high resolution and audio. Have we done it right? What things have we missed? What things are there to be done better? And right here on the introductory slide, I've got some references, 5 references to papers that were done by Peter Craven and myself. You don't have to write that down. You can take a screen grab, but we'll share this with you later. A lot of the information in here refers to these, and the many references in those papers make good reading for the background to the general topics. So without further ado, because there's a lot to deal with, I'm going to start. Okay, so my background is I'm an audio engineer, but I'm also a student of the auditory sciences. And the auditory sciences are critical if you really want to understand how to design, how to measure, how to qualify a piece of audio engineering. And when I began, there was just psychoacoustics, really. And psychoacoustics is the original branch of auditory sciences, classical science that bridges engineering with our experiences, in particular what it does. The sort of analytic approach is to treat the human as a black box, and we feed in pure tones and hisses and beeps and measure what happens. And as we'll see as we go through this a bit further, auditory sciences evolved with the rise of neuroscience. Neuroscience was always there, but it's now become more possible to do many more interesting things in this area. And neuroscience tends to look at how it works, and really to take a neuroethological approach rather than applying signals to the organism to see how it works. We study how the listening or other modes happen, dealing with natural signals, the signals that in fact the creature has evolved to deal with. Now, our hearing system exhibits many nonlinear aspects, and for example, when we encode intensity of sound to loudness, it's nonlinear. When we encode frequency to the subjective element of pitch, it's nonlinear. Our frequency response isn't flat. The hearing system introduces distortion, and one of the biggest nonlinearities of all is thresholding. There are sounds, there's a level below which we can't hear something. That's an ultimate threshold of ultimate nonlinearity. And these aspects of hearing led to, over several decades, a kind of sense amongst audio engineers that it was very easy to fool the ears. But that is not my perspective. I've worked on this for maybe almost 5 decades in audio engineering. And the more we do, the more we come to respect how incredibly subtle and sophisticated the human hearing system is. So other nonlinearities in here are the auditory filters, the way in which we can select frequencies in bands. We'll talk about that a little bit further, and the way that leads to masking. But another way in which the human hearing system is nonlinear is that our time frequency discrimination doesn't comply with the Fourier limit. So, because there are nonlinearities, superposition can't be relied upon, and that's a key point, because it means we can't do an experiment to test for A, an experiment to test for B, and then imagine that if we put A and B together, we're going to get the result of A plus B. That's not going to happen. So testing the human and testing our hearing is a very sophisticated problem and a subtle problem. Now, one of the hearing thresholds that we have is shown here. Let's find my mouse. So the blue curve shows the minimum audible field, which for a pure tone is the average threshold of hearing at different frequencies. And you see that our ears are most sensitive 4 kilohertz, being progressively less sensitive at low frequencies. And there's a number of reasons for that, some of which are to do with basic physiological noise, blood flow and so on, but also to do with the mechanics of the outer ear. And our hearing drops off rapidly towards 20 kilohertz for pure tones. Now, the red curve, which is shown under this, is a different kind of threshold, and it's an interesting one when we're trying to discuss information graphs and the amount of information that can be encoded. And you'll see that as we go forward. Basically, what this threshold is if you can imagine a shaped noise which follows this spectral curve, which, when we raise it sufficiently loudly, it becomes uniformly exciting at all frequencies. In other words, when it's too quiet, we hear nothing. Turn it up a bit, we hear it at all frequencies simultaneously. This is a very important concept, because it shows us the basic fundamental sensitivity of the hearing system. And the reason we use this is that if we have signals that are not just a pure tone, let's say a pure tone at 1 kilohertz because we're audio engineers, but we've got a noise spectrum, then the threshold is going to lie between the red curve and the blue curve. Okay, so now let's look a little bit at auditory channel information capacity from a psychoacoustic point of view. So this graph, which is on a dB linear versus frequency linear, this is a Shannon diagram, replots the uniformly exciting noise at threshold for the human listener. And on this graph, we've also got some interesting fixed points. One is this brown curve, which is the thermal limit for a microphone. This is quite an important limit because it's the absolute minimum that we can record or transmit. A microphone cannot pick up a sound which is quieter than that. And that was from a derivation which is one of the references I'll show you. But the thermal limit, we like to think of this as absolute zero for sound on planet Earth. By the way, on Mars it's much lower, but that's another thing. Another fixed reference point here is environmental noise. So this is taken from a recording made of the sound of the outside world. It has a particular spectrum, but that is these are fixed points. Now, also on this diagram, I've shown the minimum noise in a recording that we found in a large survey of high-resolution recordings. In other words, which recording's got the quietest background noise? This is it. This is its spectrum. And it's shown at a very high playback level. This is something that we talk about, is the acoustic gain of an experience. Basically, what 120 dBs means is the volume control is so high that a full-scale signal would give us 120 dB signal. That is really very, very loud. But 120 is used because that is the maximum That's the threshold of pain for the human listener. On this diagram, in addition to the minimum recording noise, I've plotted the channel capabilities for some popular carriers. So for example, the CD here, shown in the green box, this is the coding space for a compact disc at that playback level. And the blue rectangle shows the coding space for 9624. And you'll notice a couple of interesting things. One is 9624 goes way beyond our nominal capability of frequency, and also, of course, goes below absolute zero for the human listener. Sorry, for planet Earth. And then this even bigger rectangle is for 32 bits, 96 kilohertz, and we'll talk about the sanity of that later. Now, obviously, this is a high level of playback. If we lower the level to 108 dB, so we dropped it a couple of bits, you'll see that as I do that, the thermal limit and the environmental noise doesn't change, and nor does the human threshold, but our channel is perhaps better matched, the CD channel is better matched, and so on. And just because this is a Shannon diagram, data rate is proportional to area. So inside the CD box, 16 bits, 44.1, for one channel, the area of this box is equivalent to 707 kilobits per second, whereas 9624 is 2.3 megabits per second. Now, at this level, and why did we pick 108 dBs? Well, that is the typical acoustic gain for what we would call an audiophile demo. Someone who's very interested in high quality sound will tend to play it at this sort of level. And in fact, if you're trying to play at realistic acoustic level, playback something like a string quartet, you'd often find that the channel gain is set to 108 dB. So it's a little bit loud, but it's natural. And at 108, we've got a better match here. And just to continue with the discussion about data rates and so on, the area of the uniformly exciting noise at threshold is 750 kilobits per second, but actually the whole acoustic world is brought to a finite level at the ear with a data rate of 706 kilobits per second, because we don't have any receptors above 18 kilohertz. So 706 kilobits per second is sort of the information capability of each ear. That's sort of confounded by masking, because one of the things about an information channel, or let's say a transmission channel, is it should be able to transmit loud signals and quiet signals, but the ear will not receive quiet signals in the presence of very loud signals. All right. Now, if we move on and we turn the gain down again to 102, and 102 dB acoustic gain is the kind of level that we would find a large number of professional mastering engineers are working at. This is the kind of sound pressure level that you can listen to all day and not tire your ears. And also, interestingly, as we get down to these levels, our ears become more and more sensitive. So we don't really lose anything in terms of trying to hear differences at 102 to 108. Okay, that's sort of basic psychoacoustic perspective, and we're looking at some numbers here of the amount of data capacity it takes to deliver a signal into these channels. Okay, now that was a Shannon diagram. We use linear frequency. Here is a human perspective of the same sort of thing. Human perspective, our hearing is broadly logarithmic in terms of intensity, in terms of level, but it's also broadly logarithmic in terms of frequency. So the picture changes the shape, but the same things are there. Although now, interestingly, on the log scale, the thermal limit, absolute zero, we see this as a straight line. And on here, we've drawn a few things like not only the CD channel, but noise shape channels. Noise shaping is a technique which can be used to minimize audibility or to improve convergence on a noise floor of a signal. We'll come back to that a bit later on. And in here, a couple of other things. The orange curve at 108 dB is the noise floor of a silent groove of an LP disc. So a vinyl disc has a much higher background noise than a digital channel, but it's not entirely inappropriate because remember, this is the uniformly exciting noise at threshold, whereas the tone threshold is somewhere around here. And that comes to another point. Very quiet recordings, or the background noise in recordings, will often end up in this region, somewhere like 90 dBs down on full scale. And this is an area where the human listener can be extremely sensitive. Now, I made a note here about Cologne, the concert in Cologne. For some reason, the curve's gone missing, but it should be sitting about here. And this is a piece of music where if we listen to it on a system which is introducing distortion, quantization noise, there's blur in the system, we'll not hear anything other than the fact that there's an audience present. But if the system's working well, we will hear the audience. Not only will we hear them, we can hear what they're saying. So our ability to discriminate very small amounts of detail at this level is important. But the bizarre thing about digital audio is it's really poorly matched to our hearing system in the sense that, for example, if you have a 16-bit channel, we've got 32,000 steps on the ladder. The top 32,000 steps are all taken up in this 6 dB, and then we got 16,000 steps here. But by the time we're down here, as we'll see later, just 10 steps on the ladder is reproducing this information. So it's very important that we handle the data properly. So I've talked about this. We're now going to talk a little bit about the neuroscience and where that takes us. Inside our ear, I think this picture here, yes, here's the outer ear, here's the cochlea. Inside the cochlea, if we take a cross section, the business end of the transduction into neural impulses from acoustics is shown here. And we have the membrane, the basilar membrane, tectorial membrane, which vibrates in response to the sound travelling along the cochlea. The cochlea, by the way, disperses sounds from high frequencies at this end to low frequencies at the other. Inside there, we've got a number of hair cells with neurons. The inner hair cells, there's about 3,500 of these. We could think of these as the microphone. This is the point at which the sound is picked up, and this could be anywhere along the basilar membrane from the 20 kilohertz end to here down to the 60 hertz end down there. These hair cells fire, connect to neurons, and the neurons are firing at different rates. More than half of them, 61%, have quite a high spontaneous rate. So the information isn't entirely in the spikes, it's in the way that the rate changes. And each neuron will be responding to a narrow range of dynamic range, typically no more than 30 dBs out of the 90. Some of them will turn on as low as 0, some won't turn on to 70. And the maximum rate that we can see on these neurons is about 250 spikes. About a quarter of them run at a medium rate, and they're picking up not just the sensitivity, but envelope information. And about 16% of them have quite a low dynamic range, and they're mostly about protection and alert. So we have something called the middle ear reflex, for example. When a sound gets loud, and there's a very small dynamic range here, it will fire a protection mechanism in our hearing. And these different types of neurons are accumulated in the brainstem, which we'll come to in a minute. One of the most interesting things about the inner ear is here. For every inner hair cell, we typically have 3, humans sometimes up to 5 outer hair cells, which have neurons not going just to the brain, but coming back from the brain. In fact, predominantly the information flow is to the outer hair cells. And these outer hair cells actually act as motors. It's really fascinating. If you look at them under an electron microscope, you can see them moving in response to instruction from the brain. What this tells us is that the sensitivity and the tuning of our hearing is under continuous control of listening. Signals go this way, information comes this way, changes the selectivity, the gain, the bandwidth, and it's conscious. So in these neurons, temporal fine structure is encoded in phase locking, and temporal fine structure is a very important part of what we would talk about as high resolution. But temporal fine structure, anything to do with timing, is expensive because the neuron that can carry information quickly cannot be very long, or it has to be very wide. So the temporal fine structure is basically decoded in the brainstem as close to the ear as possible, not in the auditory cortex. And this next part, which we won't go into too much detail now, but basically this shows how temporal inaccuracy, that uncertainty that can happen in a single neuron, by the time they're combined, can give us a temporal acuity of around 9 microseconds, which is the limit we've seen for humans under a number of different conditions. So this is the point of action, the point where sounds are picked up, and of course there's 3,500 of these, so they're being picked up at lots of different frequencies. And here's the cochlea we've been talking about, and the ascending and the descending pathways of information. So the cochlear filters I talked about, the descending neurons, there's 1,800 of them coming from the superior olive right here in the brainstem, that's tuning the cochlea. And what's really going on here is it's selectively changing what we're listening to in response to the content, actually reaching out to listen for things. We want to listen to the flute, our ears get tuned. We want to listen to a bird, our ears are tuned. We want to listen to speech, they're tuned. And this is, we don't realize this is happening, but it's continuously happening. I think as many recording engineers would love to have a microphone that could be adjusted in that way. On the way up, this basic information of, we've got maybe 10,000, we could have maybe up to 2 kilobits per second of information, 2 kilospikes per second, each spike's approximately 3 bits. So 6 kilobits of information could travel from the cochlea to these nuclei. Very quickly, that data rate is reduced. And it's reduced because what's going on is we're not feeding all the information about frequencies, but features are extracted. Features like stop and start. Is the frequency going up or down? How loud is it? What's its envelope? The envelope of the sound is almost as important as the frequencies, and the temporal fine structure of the particularly in the frequency domain is another key part of the information, because what's going on is we want to know not what is the frequency and what's the level, we want to know what's out there. And so the features are extracted, and information reduction is a requirement, not a side effect of perception, because by the time we reach the brain, things are happening slower and we don't want information overload. So this is just another picture of the ascending pathways. I think we'll move on, except to say that although neuroscience has made a lot of progress, people studying information science in neuroscience, auditory neuroscience, still believe we're very much at the early stages. It's still what's called a needle in a haystack. But there's growing evidence that shows that the neural structures maximize metabolic efficiency rather than information. In almost all creatures, the fitness of the neural processing structures tends to fit Darwinian efficiency per joule. Every neuron takes energy, every click takes energy, every process takes energy, and it's a highly refined system. Okay. So let's look now at auditory information flow. In the outside world, we're going to have a lot of things that are making noise. It could be musical instruments, it can be chiming clocks, it could be whatever it is. These sounds, come to the periphery, and they're encoded frequency and time, envelope, stop, start. And as we go up, the process of scene analysis happens. So the first level of auditory processing is what's out there, and then the next one is we pay attention to it. We decide we're going to listen to one thing. And one thing we take takes dominance. We can change that by deciding what to listen to, but other sounds can grab our attention. And then finally we get up to perception. What is it? What are we listening to? So that's the sort of basic information flow. While we're talking about this, we talked about 700 kilobits per second is the information capacity of the auditory channel in the ear. Very different levels of information go on when we're talking at higher levels. This is a diagram which comes from Weiss's paper of information flow in speech. We have a thought, we turn it to language, we instruct the speech comes out, signal travels, and the decomposition happens in the listener. And just to give you some idea of what is considered maximum data rate for cognition, 52 bits per second, a very low number. In other words, although the information is coming across, it's not all coming across all of the time and instantaneously. We form a picture. Someone's talking to us, we know who they are. We've worked that out. What are they saying? The sounds in the room, those are other things. We can listen to up to 4 things at once. But the data rate for acoustic speech is about 35 bits per second, which is way less than the sort of data rate we tend to use for digital audio. Okay. Key point here is that our hearing is evolved primarily for survival. Of course, social interaction is important, the ability to speak, to communicate with each other, to communicate over distances, round corners, communicate in the dark. Hearing is a very important sense. But the fundamental neural processes in the way we hear are born in the natural world. And the sounds of the natural world obviously include rain, wind, snapping twigs, the sounds of the outside world, and in addition, of course, the sounds of other creatures, animals, birds, bird songs, and human speaking. Turns out all of these songs have some common facts. One is a 1/f type function. The environmental sound is almost exactly 1/f. This is a recording we made. It's an extremely accurate fit. It looks almost like a cheat, but it isn't. This is a bird song on top. But other types of natural sounds tend to have these kind of fractal spectral viewpoint. So it rolls off here 1/f, and this is rolling off faster. Probably this recording of a breaking wave, a sea wave, probably because the microphone was rolling off. But the self-similarity in natural and environmental sounds means that we don't have a perfect match to either analog recorders or particularly to digital recorders, and we'll come to that in a minute. One of the things we are familiar with, very familiar with, it's hardwired into us, is the way that sound travels in air. Everything we hear comes in air, whether it's however it's been sent to you. And air attenuates sound, air dims sound, but it is causal. The output never comes out before the input. Sound, pulse, if you have an impulse, the sound rises and falls. And the further we are away, the more high frequencies are attenuated. You know this, you know what it's like if you hear a lightning strike nearby or if you hear it a long way away. It's you put your head under the lid of a piano, it's brilliant. If you step away, it's dimmed. And air changes everything. So in some ways, some of our goals to be lossless are made pointless by air itself. However, air is very transparent and we know it and we allow for it. And as such, for us, actually, air is transparent. Finally, on this section of the talk, I want to talk about particularly timing information. And one of the things that has become clear, certainly in the last 2 decades or even less than that, is that our hearing is more sensitive to timing than we thought. When I got into audio, when I was taught, BBC audio, we thought human could hear 20 to 20 kilohertz. That meant that we had a 50 microsecond approximately time discrimination. Now, it turns out some very useful papers from Oppenheim and Magnasko and work which has been followed up and repeated elsewhere, this Polish group here, show that the human, in fact, exceeds the Fourier uncertainty limit by between 5 and 50 times. We can discriminate time more precisely than the bandwidth of our hearing system leads us to believe. That's really very, very profound and important. And being able to discriminate time and being able to separate temporal aspects of sounds is important. Obviously, in a sort of almost trivial way, separating time is important when we're listening for echoes and for reverberation, but also just subtle changes in any sound, particularly if the subtle changes are correlated to the content. So this point, and the uncertainty limit 5 to 50 is not variable randomly. Typically everyone is 5 times better. If you want to be 50 times better, you have to have studied conducting for about 20 years. And artists music artists will tend to be in the 10 to 15 region quite quickly. Anyone actually actively playing music will become better at judging time and frequency simultaneously. And this is just a random aside. The aspect of time frequency analysis was studied in great depth by Lewicki. Here we have his key paper from 2002, in which he was able to show through neural modeling how the hearing system might work. And basically time frequency analysis can be done in a number of ways. A shows us the Fourier method, where we can analyze from minus infinity to plus infinity time, and we get a very narrow separation of frequencies, but we have 0 time resolution. We can use wavelets. The way that the human hearing system appears to work is that by changing the function of the cochlea for efficient coding of environmental sounds, we end up with time frequency pictures like this, where time is quite accurately recorded at high frequencies, frequencies more important at lower frequencies. When listening to animal vocalizations, it's a particularly birdsong, frequency is more important than time. So we stretch it out. We have a different transient capability of our neural system. And speech is somewhere in between. Speech probably came last, but it's another mode of using our hearing system. And in backward modelling this, what Lewicki showed was that the auditory filters, if you imagine the sort of notional filters in the basilar membrane, have impulse responses which change according to whether we're listening to environmental sounds or animal vocalizations and speech. Now, this is important because it's one of the areas I talked about earlier about our hearing is nonlinear. It's very difficult to do an experiment if the listener is going to change the mechanism on you. And some of the things that were done in the early days with lossy codecs, for example, were based on measurements made of auditory filters in one of these fixed conditions, and it does not apply everywhere. So that just shows the auditory filters. And if we play all this backwards, talking about low data rates, he also showed that by using these kind of kernels here and spikes, we could build a codec that had very, very low data rate. Here's the input and the output, and the word canteen was used, probably because they were hungry, and he showed how in 60 neural spikes, which is about 180 bits, they could code the word and have a very low residual in the output. Now, why is that important? Well, it just sort of tests the model. But this kind of coding turns out to be, especially at low bit rates, 20 dBs more effective, 20 dB lower signal to noise ratio, if you like, than a Fourier transform method. So, and here we are, playing all this back, cross-check of the modeling, predicted auditory bandwidth for the different sounds. And it turns out that for speech sounds we have this, for vocalizations we have this one, and when the auditory filter was independently checked by the German and Cambridge psychoacousticians, the Moore study and Zwicker study, they ended up with similar numbers for the effective bandwidth of the auditory filter. One of the problems about the auditory filter, of course, is once again it's nonlinear. The width of the filter changes. It's more narrow when the sound is quiet, and it's wider when the sound is louder. Okay. Just out of curiosity, when we put that together and we model what the auditory filter tells us about straightforward measures, we see the existence region for distortion, we're most sensitive around 60 dB sound pressure level. Anyway, so I'm going to move on because we're running a bit slow here. Neuroscience also is telling us with brain scanning more and more information. Things like fMRI, PET widens the view we have, and EEG also widens the view. And in some studies on high resolution using EEG is beginning to give us clues that things are happening in the brainstem when we listen to particularly high frequency sounds that don't actually make it to the cortex. In other words, it seems that the information is extracted. Maybe it's timing information, not frequency information, and goes forward. Now, obviously, when we listen, we don't hear whistles and squeaks. We don't hear tones. We hear things. Absolutely, we hear things, and the different sonic cues, I've listed them here: amplitude, location, frequency, pattern, rhythm, go together to give us an object. Now, if I showed you this, you wouldn't be able to say what this was. But if I was able to start playing this, and by the way, I'm not going to play it because we figured out that trying to play high quality audio over a Zoom call is somewhat pointless. But when the music starts, within 1 second, you know what it is. And you'll all have had this experience. The music starts, you're not hearing tones and things. You hear a piano, you hear a violin, instantly you know what kind of room it's in, you've got some sense of the acoustic, and this extraordinary process by which a very small amount of data entering the ears, features are extracted, and the more features are extracted, it's obviously a feedback loop, and so we can listen, well, is that a cello? We can tune our ears to be sure of it, focus on one thing at a time, build up a scene. And if you know the music, you'll know the composer. So this extraordinary nonlinearity that sounds come in and we hear things and we externalize things is a key feature of our hearing. And if you think about that, that's using memory. Memory's critical. We've got a short-term auditory memory. We're holding a few seconds in our memory bank. We have the long-term memory of what are things. Here's a hypothetical decision tree. We hear something, we think it's a keyboard. You might have enough signal-to-noise ratio to know immediately that it's a piano and not an electric keyboard. But then, if you know something about it, you could fairly quickly work out, is it a large one or a small one, and even what brand it is. This is a slightly old slide. It doesn't have a Fazioli on it, but the point's there. The more you know, the more memory we have, the clearer picture we can build up. And this is rather like in the way vision works, where the data rate coming in is quite low, but we build up a picture with something like this. Once we know it's a piano of a certain type, that's the piano, and we figure out the other instruments and what are they playing. So the information flow and the cues that we need to work these things out are critical. And when we come to make the recording, the challenge has always been, well, what is it that we should be capturing? Okay, so in recording, our target obviously is the sound of the original. And in the old days, we had a microphone and a loudspeaker. And that is actually the straightest line we can have. The best sound you can probably have is listening to that microphone directly. Microphones are lossy. It's got problems. The speaker's lossy too. But in analog systems, there is noise and there is temporal blur, but it's natural. We could record it here on an analog recorder. The best we can really do is aim for transparency. The kind of things that go wrong in an analog recorder are natural for reasons we'll talk about in a minute. Now we come to digital. In the digital world, the proposition is this. We've inserted this channel in the middle of the analog chain. Nothing's perfect up to here, nothing's perfect up to here. The idea of digital is that it can do two things that it's very hard to do with analog. One is we can transmit it through time and space, and the data we can move without losing it. And playback can be repeatable. And if we're lucky, the recording won't deteriorate. And if we're careful, the processing we do in the digital domain can be transparent, but it's very rare that it would be transparent. And in fact, the biggest problem, as we'll talk about in a minute, with digital systems is how do we go from analog to digital, and how do we go from digital to analog? The converters are the gateway to success or failure. Okay, so with conventional digital, it's based on classic sampling, the reconstruction theorem. Shannon's reconstruction theorem says that if a signal contains no frequencies higher than sampling rate over 2, it's completely determined by capturing its values. And it can be reconstructed with the perfect low-pass filter. And here is the impulse response of the brick wall filter, which was so often used in the early days of digital, and indeed is still predominantly used. Filter which is a linear phase filter. Not because I think people thought linear phase was the right thing to do, but because it's lower computational cost to create it, and we kind of ended up being stuck with it. And one of the odd things about this filter, this reconstruction filter, is that it's not causal. Everything I've showed you so far, sound begins and it decays. But with the causal filter, things are happening before the sound, before the impulse, we have an envelope. And this is challenging for the human listener. We'll talk about that in a minute. When we capture the digital, we do two things. We have to bandwidth limit it, we sample it, and it's quantized to some word size. We end up with notion with steps on the waveform and a quantization error here. That quantization error, I'd love to play it to you, but it's impossible on a Zoom session. But I will try and put something in the recorded version of this so you can hear quantization distortion. It's pretty horrible if we don't deal with that. And the way we deal with it is with dither. In terms of the sampling, in terms of the filtering, this shows the impulse response of a typical filter in a A to D or D to A running at 44 kilohertz. We have the envelope building up and the decay, and in terms of energy, this is the way it decays. The signal is spread out over plus or minus 4 milliseconds, which is a ridiculous amount of time when you think that sound travels a foot in a millisecond. So it's like 8-foot uncertainty in the location of an impulse. Not that we listen to impulses, but detail is smeared over that sort of distance. And as we go at higher sample rates, this impulse response is reduced. 96 kilohertz comes down to plus minus 150 microseconds typically, and so on and so on. And it may be one of the reasons that high sample rates are preferred. Anyway, here's the quantization element of it, and this shows a sine wave quantized to a peak amplitude of 5 delta. That's 5 LSBs. This is a number we're going to come back to. We've got 5 LSBs. You see, we're going to the staircase, and the quantization error is quite large. And if, by the way, if the signal falls below the 1, of course, we end up with nothing. And the way we fix this distortion is with dither. Dither is a random signal which is applied to the quantizer. It's not a signal which is part. It's not noise part of the signal. It's added to the quantizer to linearize it. We can have basically rectangular probability distribution or triangular. We won't talk about this a lot because it's all in the dither paper. But dither is perhaps the hidden, most important thing about digital audio that is got wrong every single day. That's why we called our paper The Gentle Art of Dither. Without dithering, this low-level signal produces all of these distortion harmonics. And we apply the dither, there are no distortion harmonics. It's kind of magic in the way it works. It works because of averaging, and it turns out that the averaging in our hearing system and in our eardrums and in the transducers we're using are similar. So the dither works. It's the one thing that works for our measuring instruments in the same way as it works for our ears. But dither does another thing. It actually allows us to record signals below the LSB. So back to this picture. Here's the signal. In a 16-bit channel, below 96, it would be gone. But we can find it, here in this example, at minus 110 dB. Way down. The dither allows us to see the signals all the way down to the bottom. And that's really important. So decays, which are so important, things like reverberation, which is important, we hear it all the way down. So when we go at higher speeds, we have the same sort of thing, except at higher speeds we have the opportunity to shape the dither as we'd like to do. So we can, noise shaping theorem allows us to lower the noise floor over a certain frequency range and boost it over others. So we hear a 4-bit advantage from this particular noise shaper. And if we use subtractive dither is when we are able to take the dither away at the end, and that's something that we use in the MQA process. It gives you almost perfect linearity and a lower noise floor. In situations where quantizations happen by mistake, and this is like almost everywhere, as I'll show you in a picture in a moment. It tends to be that even in a 24-bit system, we end up with quantization errors, and these errors impact our impression because our hearing system, in addition to pulling out features of envelope and so on, is also doing correlation. It's doing correlation over a window. And signals that move, errors that move along with the signal become attached to it. So one of the things that would happen quite commonly if we have low sample rate or unquantized quantizer which is not dithered somewhere in the chain, is that low frequencies will start to sound soft because the modulation noise is added to it. So here then, slightly more complicated picture, but just showing that 5 plus or minus 5, that's 10 LSB signal, minus 79 dB sitting here. There are the harmonics sitting between these two curves. We know we can hear it. It becomes very clear that we can hear it. This is shown at a gain of 108 dB SPL. So one 16-bit quantization is completely obvious. Turns out that quantizations at 20 or 21 bits are also audible in critical listening because of the correlation and the smear. Now, I've talked a little bit about sample rates, and this is just an arm waving picture to give a sort of impression of what people might tell you about using higher sample rates. I mean, theoretically, as we know, to have 20 kilohertz bandwidth, we don't need to go faster than 44 kilohertz. But because of the filters and because of our ability to discriminate time more accurately than frequency, we do turn out to need higher sample rates. And one of the reasons that higher sample rates are preferred is that the faster you make it go, the smaller the errors. The impulse response is narrow at 96 compared to 44. It's even narrow at 192. But this is a horrible picture because it shows us that we're using an enormous amount of data to get small increments in sound quality. And in the most critical listening, studio listening, we'll find that it continues to get better and we get up to these levels. But it's really, really bad engineering to use 4, 5 times, 6 times, 7 times the amount of data that is theoretically necessary to convey the data. We'll talk about that in a minute. One of the reasons that we think high sample rates are preferred is because of the way converters tend to work themselves. Now, converters can work in a number of ways, but it turns out that maybe 99.999% of DACs built on the delta sigma structure, as are ADCs. And the common feature they have is that there's a modulator which is running very fast. Maybe it's running at 12 megahertz. Maybe it's running at, maybe in this picture, 12 megahertz. 1 to 4 bits, so a small number of bits, very high frequency sampling. And the way the converter works is it's decimated. It's divided down to these different frequencies. And as it divides down, it's going through filters which give it a longer and longer impulse response. And as we divide down, the data rate comes down. By the time we're down here, we've been through 4 or 5 stages of arithmetic, been through filters. The data rate's very much lower. And then on the playback side, the reverse happens. Whatever frequency comes in, it's upsampled to a modulator which is running again at high speed. Obviously, the perfect thing to do is to connect them together, but it takes a lot of data. And the lower we go, the less data we need to transmit the audio. But we've been through arithmetic steps, and if each of these steps is not properly dithered, we have added modulation noise and blur to the sound in addition to the ringing which appears. Okay, so what do we do about this? Well, this diagram shows a somewhat bleak view, but it's a realistic view of the journey from a studio of the A to D converter, which I just showed you, I've turned it round, to a DAC in your playback system. And what's going on is that we have production, so we have a workstation which has got floating point conversion, it's got mixing, floating point conversion, back again. Both of these are a nightmare. Jane B. Angus and I will be giving a paper about this in the October AES. You've got mixing and mastering, and then converting it to PCM. Each of these steps, wherever there is a processing step, there's a requantization. If we do not apply dither, we introduce modulation noise that attaches to the signal. And when it comes to playback, the playback system could be very simple, or it could use sample rate conversion, or it could use equalization or room correction or volume control in the digital domain, and so on and so on. Each of these steps is a processing step, and again in the DAC. So what we show here is actually 17 places where it can go wrong between the microphone and the loudspeaker in the digital domain. Very, very rare for these to be perfect. It's often not perfect in the DAC. Why? Because to fix it, you've got to add dither. You add dither, it adds noise, specification of the DAC changes. Right? And if we, I once again refer to the dither paper, but if we see stages where there are quantizers appearing in one step and then, we've got quantization maybe here and then another one here, another one here. The quantization distortion builds up a very granular structure, and a structure which is very correlated to the signal, and our hearing system will pull this out as a roughness in the sound. And there's a couple of examples of where even in the workstation, trying to do it right, we can detect quantization errors in the workstations. Another thing that is somewhat depressing is that if we have even a perfect A to D converter and the dither has been used and we end up with something which is the sort of graphic equivalent of a vector graphic because it's perfectly joined together, when we do a process, turn it into a bitmap, if we don't dither it, then we can reveal the kernel of any filtering upstream. So here's the kernel of the A to D converter, which if the signal hits a 16-bit quantizer, any quantizer, in this example it's 16-bit, without dither, we see quantization noise corresponding to the length of the filter. And this noise, this modulation noise, has this kind of spectrum. So it's not that we're listening to the ringing or the high frequencies, but the noise itself is changing in response to the width of the filter that is being revealed downstream by the quantizer. This is why it's so important to keep the signal clean, and why in the MQA process we're ruthless about maintaining linearity from the point of capture to the point of playback. Okay, now I'm certainly running slow on my slides, so we'll not spend too much time on this one. Just to say that looking at high sample rate recordings, you would say, well, why is it the human can hear up to 20 kilohertz? Why do we want to capture at 96? And why do we want to capture at 192? And the answer is, we do. If there's something wrong, particularly if there's a quantizer not right, it's much better to use higher sample rates because the noise from it will be lower. It'll have a different frequency distribution. But also there are some elements that we do want to capture to maintain the temporal fine structure of the original recording. So this is kind of shown in octaves. Half the data rate of 192.24 is looking at signals above 48 kilohertz. This is signals above most microphones' capability of capturing and above most tweeters' ability to reproduce. If we cast this now onto a Shannon diagram, let's take a piece of music where we have the peak level of the music and the noise floor of the recording, average noise and average noise floor and the peak noise floor, we see that most recordings, think back to what I said about all sounds, all natural sounds, tend to have a 1/f type frequency spectrum. They also have a noise floor which is way above the bottom of a 24-bit channel. They've got a lot of coding capacity down here. At some point, typically, the content and the noise converge, and we'd end up with just the noise, which is an artifact of the fact that we're going at a high sample rate. This is noise. It actually doesn't convey any salient information, because salient information involves change. It involves, somewhere between the peak and the noise, the content is changing. If it's not changing, there is nothing there. And of course, we don't hear these frequencies. And the area of that triangle, by the way, is 850 kilobits per second, but the whole 192.24 channel is 4.6 megabits per second. If we use lossless compression discards everything above the top line, but it preserves all of this area. It still preserves these areas here perfectly. If we use lossy compression, which is based on masking, think what I said about the auditory filter. The presence of a tone means that we don't hear so clearly things each side of it. And this is sort of the fundamental principle that things like MP3 work on. But if we've only got 192 kilobits per second to convey the information, there's a very small amount of data which is actually conveyed in the picture shown here. And this is all discarded in a lossy compression. So we're showing extremes here of lossless, which is preserving sounds below absolute zero, and lossy there. So I want to talk a little bit about resolution. I realize I'm already over time, but I'll keep going. There are standards for high resolution which were set by Japan Audio Society and RIA. There are definitions. There is research into high resolution, but not a lot, not as much as we would have liked, not as much as into other aspects of auditory theory. We have some ongoing research at our company. There are academic research on listening tests, including functional MRI and EEG, happening at Queen Mary, Osaka University, McGill, and others, Tokyo University of the Arts. Japan is a center of brain scanning auditory testing. And when we think about high resolution, some people say, well, high resolution is 24 bits, or it's 192, or it's lossless. Actually, it's none of these things. But the theories of high resolution, the 7 theories that we talked about at the beginning, are basically this. People would say, because high sample rates sound better, it must be that high frequencies matter. A lot of testing's been done on that, and the basic conclusion is this is not true. We don't prefer high sample rates because of the higher frequencies that come out of it. Several experiments have done to prove this, but maybe the most convincing test of this is our personal experience working with artists, even with rock musicians, who for various reasons have abused their hearing and can't hear anything above 9 kilohertz, but they absolutely can tell the difference between 192 and 48 kilohertz sampling rates. These high frequencies really only matter when they're correlated to the baseband, and so this theory is not given dominance, at least in our world. However, high sample rates do lead to slower, shorter filters. We can have shorter filters, we can have lower impact. The shorter filter blurs less in the converters and the mastering, and these filters are audible absolutely. So this one sticks. Another theory about high resolution, people would say, well, actually, intermodulation distortion means that you will hear high sample rates, and it's a bad thing. Our paper in the 2019 journal completely showed that to be not true. Intermodulation distortion between really high frequency sounds and audio sounds is not in the real world a practical matter to worry about. So this is not a valid theory for why people may prefer higher sample rates. But in the time domain, higher sample rates do give us better temporal resolution. We can choose which filters we use, and if we're smart, we use dither to keep the modulation noise low. And so that's very much a factor. And by the way, quite interesting, when we're talking about human 5 times broadly more sensitive to time than to frequency, this is not true if sounds are going backwards. Our neural system is hardwired to sounds that start and decay. And if they go backwards, just try playing a recording of a piano backwards, you'll get some sense of what I'm talking about. It's completely unnatural. Our neural system is not programmed to look for sounds that behave that way. So anyway, time domain is important. And in the amplitude domain, modulation noise reduces with higher sample rates. Modulation noise from missing, dither, predominantly, or from inaccurate converter A to D or D to A. So, exactly. And so we come to this, that once we've eliminated the theories that don't matter, where we come to is in the human domain is that time's more important than frequency. Feature extraction and object formation means we really want short filters and we want zero modulation noise. An adequate coding space is all we need to get that information across. We don't need to encode sounds that are below silence, and we don't need to encode sounds that don't exist. So this ultimate viewpoint, which is really just a pointer, because this is a long journey, a long journey of generations of figuring out exactly how to capture sound most accurately for humans. I prefer to use the word resolution in the way it's used in the optical domain. Resolution to resolve or to separate. It's not high resolution because it's 24 bits or 32 bits or 192. But a system can resolve if it can separate sounds, and it's an attribute. We feel it's an attribute of a complete system in the analog domain, from the microphone to the speaker. 2 sounds close together remain separable by the listener. Then we will hear the reverberation clearly. We will hear the location where the sound is. We can hear more clearly the fine decays of the instruments in the sound. So the key thing is resolution can't be guaranteed by sample rate or bit depth. There are some great sounding recordings at 4416. There are some horrible ones at 192.24. It simply is a very poor proxy. We just have to look at the bandwidth and the dynamic range, temporal blur and noise modulation. And that the project that we've been doing on MQA is doing that. It's considering not just the digital path, but how we can deconvolve back to the analog on the A to D side and deconvolve the DAC back to the analog on this side and transmit salient information with very high precision and not salient information with less precision, because that's good engineering practice. So here we are. The way this approach is done is, here's the spectral content of music. This is a large corpus of music, looking at the peak levels that we find and looking at the noise levels that we find. And I think the next slide, it's fascinating because, mastering engineers, recording engineers, audiophiles sometimes say, well, actually 24 bits not enough, we need 32 bits. But when we come to look at the recordings, and in the MQA project we've encoded now something in excess of 20 million songs. And our encoder has an analysis, a record of every one. And one of the things we pulled out of the analysis was, tell us what is the minimum noise level in the band up to 20 kilohertz in bits in commercial 24-bit recordings. And this is the answer we got. Half of them have a noise floor which is worse than 11 bits. That's not necessarily bad, because we're talking here about maybe old and analog recordings, but very, very beautiful recordings that sound high resolution to us. Things like from the 50s, MJQ, that sort of thing. Many recordings which have a lot of stems, maybe you've got 100 microphones, a lot of mixing, the noise floor is always going to be up in this region because of the noise coming from the microphones and the electronics themselves. When we look at the very best recordings, almost none have a noise floor as low as 18 bits. And those tend to be single microphone, straight to the A to D, and we measure the content. We can tell you which these recordings are, but they are very rare. But the key point is that we're not looking to need a noise floor of 24 or 32 or 64 bits. More to the point, we have to make sure that we can get this information correctly across. And when we combine the peak levels, sorry, being a bit oversensitive here, when we combine peak levels with the noise floor, we find that every recording typically produces this triangular shape. This is very important, because the Fourier transform of that, of course, is something which is not a sync with if we had a rectangular coding space, we'd have to use a brick wall filter, but we don't. We've got triangular. It depends on the particular recording how it's disposed, but we can rotate all of these pictures to give us what we need. And then we come to the point of band limiting, because if the frequency spectrum is falling continuously, we don't need a strong anti-alias filter to remove the high frequencies. So we can look at the band limiting in a different way. Shannon permits 1/fs degrees of freedom per unit time, but there are a number of things that make this invalid. Some signals are inherently not band limited. Once we've captured something in the digital domain, we've put it through processing. Quantization is not band limited. Clipping is not band limited. Dropout, etc. But if we have a finite rate of information, and that's what this picture is showing, and that's what this picture is showing, we can make it work with different kernels. We don't have to use the rectangular kernel with the sync. We can use something like this. This is a Gaussian, very slow roll-off. This is what's used in optical, in picture imaging, because we can't tolerate the gain, the active part, which flattens the response, gives us the undershoot. But something like this is appropriate for an audio channel. And Peter and I showed that you could use different sampling kernels. We've got no time to go into this, but look at it in the hierarchical paper. By using what's called B-spline system, we're able to build a system which has an end-to-end impulse response like that, allows us to have around 10 microseconds resolution when it's transmitted effectively at 48 kilohertz, although actually the transmission rate is 96 because of the way we fold it. But when you've got a system that has that impulse response from analog in to analog out, then, sorry, mouse is being a bit sensitive, then we can look at this in this perspective. Here is the impulse response of the digital chain and compare it with air, with different columns of air. And with this channel, with the MQA channel, we can resolve sounds that are 8 microseconds apart. And this is an example, in fact, of resolving. So resolution, separating sounds. Imagine we've got two sounds here, here and here, and the brown curve shows what air would do given these two impulses. Air will follow it. And this coding system, using the B-spline, can allow us to separate them. We can end up with two separate events. And providing we dither it properly, and particularly if we use subtractive dither, then we end up with an extremely transparent system from the listener's point of view. And just to show a few things here in comparison, the brown curve is the impulse response, magnitude response of 192.24, good converter, but sounds are smeared over a couple of hundred microseconds in each direction. Depends where we want to cut it, maybe 100 microseconds if we look at it here. Air does this. Nothing comes before the signal. Air decays. And this is the CD channel, which actually goes on and on right out to the end for 4 milliseconds. So we can build a channel, we can build a coding system that introduces less smear in the time domain and still is perfectly flat and low distortion in the frequency domain. And the final thing in here that shows us, if we're careful, is that we use the right kinds of dither. Once again, I'll refer you to the dither paper, but we show here that certain kinds of dither, for example, rectangular dither, never converges, never stabilizes. TPDF will always stabilize, but depending on the type of dither, the way it's generated or the way it's shaped, we get convergence. Now this is 2 to the n samples, so approximately 1,000 samples. The error of a single quantization reduces to 0. If we have a noise shaper, we can end up with lower errors, and once again, convergence. In this case, depending on the design of the shaper, can be 16 times quicker at converging than the other. 2 to the 10 samples is about a millisecond. If the quantization is always converging at that rate, the human listener will not detect that kind of thing going on. That's inherent in digital audio. Okay, so let's try and pull this all together. We just showed how it's possible to improve the time domain by considering statistics of the signal and not over-filtering because there isn't a signal there to filter, and how we could use minimum phase kernel based on B-splines. All of that improves the time domain. And we can end up with a natural envelope, meaning no pre-ringing, everything follows the event, natural envelope with matched filters and carefully crafted dithering. So these aspects allow us to capture the sound digitally in a way which is very natural. We also can avoid undithered quantizers in distribution and playback as long as we pay attention. And if we base our transmission model on air, we want the communication channel to have the same kind of response, then it's going to be more natural. So that deals with the time domain. But what about efficiency? Well, let's just go back and look again at the Shannon diagram. Remember, we showed here a piece of music. The whole channel, 192.24, can carry 4.6 megabits. It takes 4.6 megabits per second. That's per channel. And that is the area shaded on the curve. Okay. So here, this whole area is equivalent to 4.6 megabits per second. The music lives inside this triangle. That's very typical. And if it doesn't fit in the triangle, we just have to go up an octave and it will always fit in a triangle at some point. In this case, the example we showed of the Ravel string quartet, the area of the triangle is about 850 kilobits per second, which is more than a CD and definitely more than MP3 or AAC, but it's less than 4824 bits. So, and the key thing to discover here, or to remember here, is that although in terms of data, every part of this rectangle is equivalent, all the data in the box are not of equal importance. They're clearly not of equal importance. Up here, it's not changing with content. Down here, we have the audio baseband, and here, in the octave above, there is change happening, and it's representing time domain differences, elements in the time. Yes, elements in the time domain. Okay, so that's a sort of basic look at that. Let's go to the next slide and revise. And remember again that lossless compression will remove anything above the peak line. But it is indiscriminate because lossless compression has preserved all of this. It's preserved 2.9 megabits per second, but it's placing equal weight in these areas here, right? Let's look a bit tighter at the critical data. Earlier on, we looked at this region here, which is where our ears are most sensitive. This is the conventional audio band. Here, the octave above, which manifests time domain information. It moves with the signal, so it's important. And one of the things we know about this area is that although we can't hear it on its own, if we filtered all of this away and listened to this, we hear nothing. However, the process of filtering this away is nearly always audible. So this paradox that we hear it if it's gone, and we believe that this is because the time domain information which is embedded here is important to the human listener. Okay. Another thing I want to show you here is what we're calling unrelated noise. Now, it's a fact of basic psychoacoustics that we can't hear a noise buried in a noise if it's lower than 10 dB below the noise level. In other words, if we go 10 dB below the noise level and we add a noise, we won't hear it. We have to go a bit lower to hide a tone, but we'll hear a noise. And so this grey shaded area is just drawn 2 bits below the noise floor of the recording. And by doing this, we could say that actually anything in this grey shaded area is guaranteed to be inaudible for 2 reasons. One is, as it turns out, and I'll show in the next picture, this is already at the threshold of hearing. But the other is that it's noise within noise. And noise within noise is just white noise. And one fascinating thing about white noise is that we can actually replace it. We could take this block of noise out and replace it with a different set of white noise, and you would never be able to detect that had been done. Quite interesting. So you may say, well, why don't we just get rid of it altogether? Why don't we just remove all of this and reduce the amount of data in the channel? And the answer is, you might well do that for transmission, but for playback, we really do want 24 bits because it turns out that having this block of white noise down in the bottom, the bottom 8 bits, tends to improve real-world D-to-A converters because it reduces correlated jitter. So that's a sort of side effect. That's a side effect of playback, but not of transmission. Anyway, so here we have this unrelated noise at the bottom. And let's just now go to this picture, and we'll go quickly now, the origins of what we call the origami. So the piece of music is shown here again. Here's the peak level, the noise level, and the orange triangle. But this time we're showing it in the context of playing it back at an acoustic gain of 108 dB. That doesn't mean the sound is 108 dB. It just means the volume control is set so that full-scale signal would give us that. That's generally speaking not what we hear. Might hear it on the peaks, but otherwise not. So here's the music in context. Here, this line is the human tonal threshold. Sorry, jump to slide. Is the threshold for pure tones. And the threshold for pure tones is used here because we're already at the hearing threshold itself. In other words, uniformly exciting noise is not a relevant measure in this context. On this picture, then, we're also showing the 16-bit level and the fundamental digital silence, so absolute zero for air on Earth, right? That we talked about before, the minimum level for the microphone. We can imagine constructing this area in which we could bury information so long as this information looked exactly like white noise and it would have no audible consequence. And this is the origin of the origami process. Just going through it very quickly, what happens? Well, this information, the area of that is very small, can be buried in here. And the next step, we make a lossless burying, because the content in this area B is music related, directly music related, and the lossless compressor which is used puts the prediction in this region, which is the signaling region. This is the 16th bit, that's signaling that can be detected by the decoder. And then all the other lossless information goes in here, because a lossless compressor basically has a prediction and a touch-up, and the touch-up information can go in here. And you'll notice that we also folded the information as we went from this slide to this slide. We call it folding using lossless band splitting. And lossless band split again allows us to come up with this distribution file, which is 4824. The interesting thing here is that each sample is carrying 3 parts of data, not just one. It's carrying the information about the baseband, it's carrying the information about the next octave, and it's carrying information about the octave above. So we can make it do a lot more work. And we've effectively folded the data of this music by burying noise within noise and having all this available. And then you can actually listen to this, and it sounds fine without a decoder. But obviously, if we have a decoder, we can decode it. But one other thing, the reason the signaling is put here in the MQA context is the 16th bit context, is that sometimes you only have 16 bits of playback. And in that case, we end up with the baseband and the prediction of the octave above. So not everything's lost if we truncate to 16 bits. And the decoder can unfold it and so on, and we end up with the ideal response. So what we're showing here is that by considering carefully which parts of the data are actually most important, we can not only pack it into a smaller space, we can also spend more information, more of the data, getting better resolution in this area by using resolution enhancement, subtractive dither techniques. We end up with a better result here in the bottom octave, in the first octave, and we end up by being able to decode everything like that. Okay, so that's the fundamental process, and what we end up with then is being able to maintain sound quality at lower effective transmission rates, with lower data rates, and of course add to that everything that we can do to improve the time domain that we talked about earlier in this lecture. So just to summarize then, by focusing on the analog domain, and this is a key point, and from end to end, we can get closer to the actual target of capturing the original sound. By considering time more important than frequency, go back to the early stage, remember that, we can blur the envelope of the sound less, and we can set a target of 0 modulation noise, actually 0. This leads to clarity, resolution, and separation. By considering the statistics of the real world and of the music signals and natural sounds, we can also come up with, by taking information from the spectrum and dynamics, we can rethink the sampling using modified B-splines, which are more appropriate for high sample rates than the traditional brick wall. This is the basic idea. And we focus with the eras most sensitive, using crafted dither resolution enhancement. And this is just one step beyond simplistic lossless. Lossless, there's nothing wrong with lossless. It just simply transfers digital data from one place to another. But in the audio domain, what we're trying to do is to move an analog signal from one place to another and to preserve it through time, through space. And we can show that this can be done. You can pack it in a way that avoids excess baggage, because frankly speaking, to get 5 times the time domain information, time to precision compared to a frequency, we have to go at a higher sample rate. Higher sample rates uses enormous amount of data unnecessarily. So anyway, that's the summary, and I hope you all find this this very interesting. It's not just about how we do it, it's about the why and the background to sort of human neuroscience, human hearing process, and the whole idea of how we can actually capture this digitally effectively for future generations. So thank you very much for spending the time. Thank you for those who've stayed this length of time. I guess we now go to questions.
Well, thank you, Bob. That's been a very thought-provoking speech. It's kind of upsetting, really, because it kind of blows a hole in all the audio hi-fi industry. You get a CD, it's the best audio ever, and now we find out actually our ears not only are hearing things, but actually changing what we hear internally. So that for me, the fact that our ears can transmit as well as perceive is a real takeaway point. So
when we say to you, listen to this, that is actually what you do. Cocktail party, you know, somebody mentions your name, you focus on listening to an orchestra
problem, which certainly the hearing aid industry is very, very familiar with.
Yes.
Okay, so unfortunately we can't all give you an audible round of applause because we're all sitting behind our computers, but I'm seeing a lot of thanks on the chat. So I think this some people are trying to sell their hi-fi systems now. So I think it's a huge round of applause from everybody. We've had over 500 attendees on this talk, so thank you very much, everyone. We do have a number of questions popping up, so I shall just, if you give me 1 second to get the right window. So yes, as I said earlier, the Simon Blumine talk, the IT, yes, that is the son of Alan Blumine. There are a number of people who had issues with the visibility of the slides. So this talk is being recorded. It will be a high resolution version will be going on our YouTube channel. I'll post it in the chat again for everybody.
Yeah, I've recorded on this side so we can have the original.
Yeah.
To you.
I'll put it in there a few more times, but we also have a number of questions. So let's just slides. So here's a question from. Let's start with Tim Lewis asking, can you comment on the otoacoustic or emissions in relation to the motor hairs in the cochlea?
Yeah, well, that is the origin. In fact, the otoacoustic emissions typically will be heard if the active process in the ear goes unstable. And one of the things that can happen, let me go to the first slide and get to that picture. One of the things that can happen if there's been hearing damage, if you've been hearing damage, one of the things that will often be damaged are these stereocilia here. And so we can end up with too much gain. And actually that leads to tinnitus. So you can end up with whistles and beeps, or if you've taken the wrong drug or too much coffee or something. That process can fail to be mediated. So yes, and when it does, the ear actually generates sounds. You can pick them up with a microphone.
Okay, ear's transmitter.
Yes.
So Chris Coffin asks, how does this research feed into modern hearing aid design? Is that an area, is that a branch of the audio industry that you've had much interaction with?
Curiously, it's a branch of the audio industry that gets much more funding for research. The two areas that get the funding are hearing aids and how to compress the audio until you can just about bear it on your telephone. But the area of high resolution, which is where we work, which is how do we get the absolute maximum? How do we capture the performance? Not a lot of research in that. I think that if the sound is clearer, it helps, but every different hearing impairment is a special case. So we haven't spent any time on that.
Yes. Okay. Greg James asks, after throwing away all his records in the 80s, then switching over to CDs, and now he thinks that CDs sound pretty awful compared to high resolution music. Is he deceiving himself, or is there really the perception improvement going from vinyl or tape to CD to 192, 24 or whatever?
You know, the defects of vinyl are fairly clear. I mean, the benefits are it's analog. And in that sense, by that I just mean natural. So it has defects, but they're natural defects. But signal to noise ratio, wow and flutter, these are the things that made me very happy to get away from vinyl and move to CD, because digital is just bolted to the ground in terms of pitch. You know, you could get a really good playback system, because the sound CDs, if they're played back through a modern, oversampling, carefully dithered playback, can often be good. But yes, of course, high resolution files in general will be clearer.
Yeah.
Although I think any of you listening to something like Tidal will hear that what we've been able to do with the original 4416 recording is quite remarkable, by just reversing out the blur in the recording. But yeah, who knows? Keep the CDs; they'll come around. They'll be popular again. I hear youngsters are now thinking they're the thing.
Okay. Adrian Greeley is asking, why does the ear understand sound better in the real world than a recording of the same event, even though, for example, we have stereo, each ear should be receiving, you know, the recording?
Do you mean compared to being at the concert?
I think so. Yes. Yes.
Yeah.
I mean,
well, obviously, when we're at the performance, it's fully immersive. We've got two ears, but we're able to steer our hearing. We're able to hear where sounds are coming from. So, and also when you're at the live event, you can attend more easily to certain things. So it's one thing sitting in front of a pair of speakers and trying to understand a piece of music and saying, okay, that's a flute and that's an oboe. But when you can look at them, you can tune your hearing even more precisely to listen to each instrument, to understand the flow of the music. There's quite a strong connection between the visual cortex and the auditory cortex. In fact, when we swivel our eyes, our ears actually steer, believe it or not, in that direction. The eardrums move, everything to try and... So when you're actually at the event, you have cues that will allow you to understand better. When you're at the event, you're part of the event. So there's a sort of frisson excitement of being there, isn't there? Yeah, but listening to two speakers is how it was intended if it was issued as a recording.
Yeah. James Guyton asked for a link to the dither paper. I believe Sue posted a link to that in the chat, so that information is there. We can also put a link to it on the YouTube channel when this video goes live.
Yeah, and these four are the screen you're looking at now. These four, oh, so you're not looking at it. The screen you're looking at now has 4 linked papers, and they're open access, so they're free to download.
Excellent. Ian Simpson asking if this talk qualifies for IET CPD certificate. Please contact the IET about that. I believe so, but I would speak to the IET about that. Peter Veth asks, if digital recording presents so many problems in the time domain and the window where we actually listen to the music, does that mean that analog recording has superior properties?
It has different problems. I mean, the thing about digital is that if it's done right, it's exceptional. Okay, it's not a perfect match. Linear PCM is a kind of bizarre match to the logarithmic scale, but it's very convenient for DSP. But it's just like if mistakes are made on the way. In the analog system, Mistakes are made on the way. You drop the needle, you scratch the disc. There's nothing perfect, but digital can be wonderful, absolutely wonderful, providing we attend to the details.
Okay, Alex Wood is asking, how is environmental noise defined? Where do you put your microphone?
Oh, well, in this case, I put it in the garden. So literally the sound of the environment. And interestingly, anecdote for you, this is a recording that I made some years ago. And in the middle of lockdown, I did it again and found that it was 2 dBs quieter.
That's an interesting,
isn't it?
Environmental noise affects us in so many ways, and now 2 dB quieter. Interesting.
Well, I'm sure it's rising, but if you remember, the world was really quiet last spring, and the birds were busy.
Noticeably quiet.
So environmental sound, by talking about that, we're talking about the sound of the real world. Walk into the wood, all of those sounds.
Yes.
Listen to a stream, those sort of sounds.
And is it a case of if you stand still and the longer you listen to it, your perception will change as the ear-brain package tunes into it?
Yeah. And of course, we're always listening for something. We're always listening for, obviously, we're always listening for a threat, but we're also listening for what can we hear? Can we hear an animal? Can we hear a bird? Can we hear somebody talking a long way away? These sounds all add up in the environment. Are you being called to lunch?
If your stomach is empty, you're probably more tuned to such messages.
Exactly.
Steve Reese asks, for someone who is auditory in their perceptions, sound oriented, would they be doing less of the filtering in the ear, finding noisy offices distracting, for example?
The filtering in the ear is not removing sounds, it's separating frequencies. So it separates frequencies from high to low. The filtering that goes on in attention, in the brainstem, is we're trying to decide what to listen to. And that's a very active filtering process. I mean, that's why you can end up in a situation where someone's been talking to you and you didn't hear it, or suddenly you're aware of a clock striking and you can wind back in your auditory memory and say, oh yeah, that was 7 strikes of the clock. So attention drives everything.
Michael Turner asks, starts off by saying, fascinating and thought-provoking, Bob, many thanks. You mentioned a number of times the use of the conventional acausal brick wall filters in digital audio. The limited HF bandwidth of real-world signals, as you showed, would seem to suggest that we could use a much gentler filter in conventional PCM audio of whatever rate and bit depth. Is there room for better PCM simply via this route?
Yes, there's definitely. And then one of the things that's typically done is because the sample rate went up. So, when you're sampling at 44, there really are signals you have to get at 20 kilohertz. And so there's not much room. The filter has to be very narrow. But at 96 kilohertz, we can be quite more gentle. And one of the papers referred to, Peter Craven's paper, which introduces the concept of apodizing, shows that at 96K, you can have a much more gentle roll-off, which is very helpful. And in fact, that's the essence of using a B-spline filter with flattening. I mean, the system that we use for NQA, the frequency response is within a millibell up to 20 kilohertz. But the kernel is more gentle, and that's why we have a very short impulse response.
Okay, good. Bob Lord asks, curious why you use SPL values over 100 dB, presumably C-weighted, for analysis, when typical listening is done much lower. Would you relate your analysis levels to typical listening levels?
I'm not talking about how loud it is. I'm talking about what the acoustic gain is.
Right.
So when we say, in this example, the gain's 102 dB, that means that full scale signal would be 102 dB. but most of the time you're listening to it, it'll be in the 70s and 80s, right? Because the signal is not full scale all the time. If we were listening to music and the needle was stuck on 102, you'd want to leave the room. And you'd always want earplugs. Or
Yes.
And if it's 120, you could imagine you were at a rock concert, right? But yeah. So the number of 108, 107, 105 is typically the number where you would get the volume of the real thing. So if I go to a concert, in front of me, there's a string quartet, that is loud. And if I've made a recording of it, typically we get the same level playing back at these gains, but this is not the sound level. This is the theoretical maximum sound level, right? Okay. Well, it's where's the volume control? Yeah. Yeah.
Okay. Andrew Stuttle asks about, what about amplitude compression in recordings?
You mean straightforward compression?
Yes, I believe so.
It's used in two ways. It could be used in two ways. One is to raise the quiet sounds, and that was used on analog tape machines. The Dolby system is based on that. To fit the signal into the carrier that you had. And also preemphasis and deemphasis techniques were used for that. But straightforward compression, I mean loudness compression, is an artistic choice. We don't study it in our work because the philosophy here is that the most difficult thing to reproduce is the sound of real instruments in real space. It's to get a piano right, it's to get a voice right.
Yes.
In the room. If we can get that right and we have enough go in the system, then we can play a rock band and we can do what we like. But compression will always introduce distortion, fog, and modulation noise, because as we compress it, the noise floor will go up and down. And the thing that we're trying hardest to do is to stop the noise floor moving at all and keep it down here in this region where we're most sensitive, right?
Okay, I'll just answering one of the earlier questions from the IET Cambridge Chairman David Blake. For IET CPD certificates, please email camsec@gmx.com. So I think that email link is on the IET Cambridge website anyway. So it's now 8:37. So there was a few more questions, but I think I'm conscious of the time and don't want to hold people around much longer. So I think we'll bring this evening's event to a close. And so it remains for me to say again, thank you very much to Bob for a very fascinating talk. We've certainly got a lot of questions. In future times, hopefully we can have face-to-face meetings as you suggested, and afterwards we could all retire to the bar for drinks and further discussion.
Very happy to do that, Neil, but I want to thank you too for allowing me to go over, because obviously I had a lot of material here.
That's good.
And thanks to everybody for sticking with it.
Thank you. And also thank you to the IET Cambridge for helping co-host this and advertise it and push our numbers up to stratospheric heights. So again, thank you very much to Bob. Thank you very much to all of our attendees. Thank you very much to those who asked questions. And thank you for the AES for making this all come together. Good night and goodbye.